Good morning, dear students. I hope you all are doing good, and I hope that you all are taking necessary precautions so that you do not contact COVID. So, today let us look at this question from Pathfinder book. This question is from the EMI chapter, Electromagnetic Induction. So, this question was requested by one of the students in YouTube comments section. So let us first analyze this question. Okay, so there is a wooden bobbin which consists of two coaxial cylinders. The inner cylinder is of radius small r and the outer is of radius capital R. So we can see this wooden bobbin here, okay, and its inner radius is small r and its outer radius is capital R. Next, a conducting wire PQ is wrapped on the outer cylinder. Okay, so this one is the conducting wire that you see, this brown color one is there, right? So this is the conducting wire PQ. Next, is wrapped on the outer cylinder, passes through a small hole in it. So this wire, it is wrapped on the outer cylinder and it passes through a small hole in it, and then it is wrapped on the inner cylinder in the same sense. So this wire, after coming like this, it is wrapped on the inner cylinder in the same sense, and after it is wrapped on the inner cylinder, this part is held like this, the part of the wire is held like this. So this is the other end of the wire Q. Okay, now the bobbin is placed on a horizontal table where a uniform and constant magnetic field B exists parallel to the axis of the bobbin. This bobbin is now placed on a horizontal table, and in this region there is magnetic field B which is parallel to the axis. So we will take it that the direction of magnetic field B is going into the plane of paper. Okay, you can consider magnetic field B out of plane of paper also. For this question, for now we will consider it into the plane of paper. Next, if one end of the wire is fixed on the tabletop, okay, so this end P, we will fix this on the tabletop, and the other end Q is pulled horizontally with a constant velocity U as shown. So this end Q is pulled with a constant velocity U. So let us have a look at this. So this end is moved with constant velocity U. Okay, the bobbin rolls without slipping. So I want you to observe that also. This bobbin is rolling without slipping. Okay, so this bobbin is rolling without slipping. Next, an ideal voltmeter is connected between the end P and a stationary sliding contact S. So there is a voltmeter here which is connected between P and this sliding contact S. Find the moduli of electromotive forces induced in each of the coils wrapped on the bobbin. So there is one coil wrapped here, you can see, and another coil of wire which is wrapped around this. Okay, so what is the EMF induced in this coil and what is the EMF induced in this coil here? So that is the question. Let us now understand why EMF is generated within these two coils. So this coil and this coil, why EMF is generated. The magnetic field B is pointing inwards. The radius capital R of the outer cylinder, and capital N, let us assume, number of turns of the coil. The magnetic flux through this outer coil is B into area is pi r square into capital N. We can write capital N as length of the string wrapped divided by 2 pi r. So the total length of the string wrapped divided by 2 pi r gives us the number of turns. So we can write the flux equals to B pi r square, length of the string wrapped, I'm writing it L, divided by 2 pi r. Now all these quantities B, R, pi, all these are constants. The only quantity that is changing is the length wrapped. So let us have a look here. You see what is happening to this wire here, okay? So you can see the wire is unwrapping. So effectively the number of coils are decreasing as it is moving. So the EMF induced in the outer coil is d phi by dt, which is equal to Br by 2 dl by dt. Similarly, for the inner coil, we can write the rate of change of flux equals to B smaller by 2 dl dash by dt, where this L dash is nothing but the length of string wrapped on the smaller coil. So this total string wrapped on the smaller coil is L dash. Now our job would be to find out dl by dt and dl dash by dt. From that we can get what is the EMF induced in these two coils. Let us assume UC is the velocity of center of mass of the bobbin and omega is the angular velocity of the bobbin. Okay, so consider 2 points. One is A, which is the center of the bobbin, and the other is B, which is at the base of the bobbin. Now let us pull this bobbin towards right. Now I'm marking the center of the bobbin as A dash and the base of the bobbin I'm marking as B dash. We can say that this length AA dash and BB dash are equal, which means the amount of string unwrapped from the outer cylinder is the same as the distance covered by the center of mass of the cylinder. This also means the rate at which the string is unwrapped is equal to the rate at which distance is being covered by the center of mass, which means the rate of unwrapping of string equal to the velocity of center of mass. We come to a very important conclusion here, that is you see the speed of center of mass equals to dl by dt. Next, let us assume this point as A and this point as B. Now we want to find out how much of this wire is being wrapped over this smaller cylinder. What we will do is we will move along with this bobbin, okay? We will move along with this bobbin. Let us mark this end now as B dash. So we can say this is the length of the wire which has been wrapped on the bobbin. We can also say the rate at which this end has come from here to here is the rate at which the wire is being wrapped around the bobbin. The velocity of center of mass of bobbin is uc. This end of the wire is moving with u, which means with respect to the bobbin, this point has come this side with speed uc minus u. Now again we come to a very important conclusion, that is uc minus u equals to dl dash by dt. So the rate at which the string is unwrapping on the larger cylinder equals to uc. The rate at which string is wrapping on the smaller cylinder equals to uc minus u. Now we need to find dl by dt and dl dash by dt in terms of given quantities. We discussed UC was equal to dl by dt and UC minus U is equal to dl dash by dt. Let us assume this as point B and this is point A. We know that this cylinder is in pure rolling, so velocity of point B is 0. So we can write the equation UC minus capital R into omega equals to 0. Next, we also know that this point A is having a velocity U. Okay, he said the string is moved with velocity U and this is not slipping. So this point A here will have a velocity U. So we have UC minus small r into omega equals to U. Solving these two equations, we get omega equal to U by capital R minus small r and U center of mass equal to capital R U by capital R minus small r. So we have got UC and omega in terms of our given quantities. We now know the values of UC. So if we just put it here, we get the value of dl by dt and dl dash by dt. So dl by dt is Ru by capital R minus small r and dl dash by dt is small r u by capital R minus small r. We had discussed the EMF induced in the outer coil is B capital R by 2 dl by dt. We are substituting dl by dt here. We get B R square u by 2 into capital R minus small r. EMF induced in the inner coil is B small r by 2 dl dash by dt, which is equal to B small r square u by 2 into capital R minus small r. So these two are the answers for the question asked. The next question is, find the reading of the voltmeter. So what is the reading of this voltmeter? I'm assuming the magnetic field to be into the plane of paper. So for the outer cylinder, as the string is unwrapping, okay, the flux is decreasing. I want you to guess how will the EMF be induced. Similarly, in the inner cylinder, the string is wrapping. Effectively, the flux is increasing. How will the EMF be induced? See, I have represented the EMF induced with help of batteries. Okay, so just check if your guess is right or wrong. So I will just play this, have a look. So EMF outer loop is induced in this sense and in this loop it is induced in this sense. You can also see the voltmeter reading here. So we had marked this as E outer and E inner. I'm just marking this as VO and VI. So to find reading of this voltmeter, we'll use Kirchhoff loop law. So VA, I'm writing VA here and this is at same potential VA. So we're going along the wire, positive to negative terminal minus VO. Okay. Next we come enter the smaller cylinder plus VI. Okay, negative to positive, so plus VI. Going here and coming here equal to VB. So VA minus VO plus VI equals to VB. Next we substitute the value of VO and VI which we had got earlier. So VA minus VB equals to B R square U by 2 into capital R minus small r minus B small r square U divided by 2 into capital R minus small r. Finally we get the reading of voltmeter as B into capital R plus small r into U divided by 2.